All right. It's a great pleasure to have Maxim for his second talk on non-holomorphic deformations of Landau-Ginzburg models.
Okay, thank you very much. I tried my best to prepare the second lecture again with PDF, and it actually took me much more time than deliver the lecture, and I didn't accede to the very end, so maybe at the end I will do by writing on my tablet. Okay. Yeah. Okay. Just a second. Okay. Yeah. So first, I have to fix some terminology. So the spaces which I consider is usually manifolds, but we just compact Hausdorff spaces, locally compact Hausdorff spaces. And suppose I have a map from one space to another. What I call a non-critical value is a point on the base such that there exists a open neighborhood subject to heuristic the pullback of the open neighborhood get a fibration. In fibration, you can understand in the sense of what framework you are in. It's if you homotopy theory, it's sense of Serre. If it's just topology, it's continuous fibration, or smooth if you are in a manifold setting. And essentially, by definition, non-critical values form an open set. So the complement is a closed set, which is called critical values. So normally, if a map is proper, then the set of critical values is the image of set of critical points, points where my map is locally not a fibration. But if the map is not proper, the same assumption that critical values are the image of critical points holds if F has no critical points at infinity. Yeah, for example, you can imagine very stupid situation. You get like open embedding. Yeah. You remove from R point, then point which you remove will be critical value, but not value of any point. So it's a case of non-proper map, and we say that F has no critical point in infinity if you can remove some, if you consider, if you can remove some open part on which my map is a fibration, and the rest will be a proper map. So this, for example, I draw the projection of some non-compact surface to real line. There are some more critical points, but the surface is not compact, and fibers are not compact. And this yellow part, it will be this domain which we, actually it's complement to you. Sorry. Yeah. So it's a compact domain which on which have all critical points. That's outside, it's all fibration. Now, so it's just terminology. What are critical values? And in the case of just a little remark, when you have a map of manifolds, the sufficient condition not to have critical points at infinity is to have a partial compactification by manifold with a boundary. Again, the guy could be not compact when the target is not compact. So my manifold will be interiors of this partial compactification, and the map extends by continuity to proper map, and on the boundary it's a fibration. Okay, now I'll talk a little bit about critical loci for real and complex functions. So real functions, it's a simpler story, it's like Morse theory, and I think it's what I'll talk about. It's maybe called persistent homologies these days. Suppose you get a smooth or continuous map from some space, or manifold, or just locally compact Hausdorff space, to real line. So my target is just R, and assume that this set of critical values is discrete. So we can enumerate them. It could be actually infinite to the left or to the right. So you get discrete subset of real line, and for each critical value, I will associate certain object of derived category of the modules. Or I actually write its homology, so I will not use notation, so I didn't distinguish complex and homology. I can it will be jump at this point. So what do? I consider a small interval. We have point Ti. I take a small interval containing this point, this says to epsilon, and take homology of pair, pullback of this interval relative to the pullback of the left end of this interval. Yeah, so if this picture have pullback, it will be take this red domain relative to this red boundary. Yeah, if you have more singularities, then it will be one-dimensional space. But if it's not, it's something, some kind of jump. And what the structure of these jumps? First of all, one can generalize these jumps. If you see, these jumps are associated with intervals whose endpoints are not critical values. Or one can, you will see later, it's one-dimensional disks in R whose boundary doesn't contain any critical value. Yeah, so take any closed intervals, interval whose endpoints do not lie in the critical values. And then we again can consider homological pair, pullback of the interval, pullback of the left end. And obviously, the homology do not change at the continuous variation of parameters A, B, avoiding critical values. Yeah, so we got jumps up particular class of this homology when closed intervals are contained exactly one critical value inside. In general, if you have let's say 3 numbers A, B, C outside of critical values, then we get 3 intervals, and then we get 3 homology groups or complexes, and they form exact triangle. And depend how many critical values lie in between. Yeah. So what do we have? We have a collection for we have this critical values which we want to avoid. Then we get intervals with endpoints avoiding these guys, and we get this exact triangle structure. Yeah, so this thinks it's essentially pure representation of A and Q, where N is the number of critical values and some kind of limit when N when we get infinitely many critical values. So there is some asymmetry here. We take homology relative to the left endpoint of the interval. The same story one can develop and have a right endpoint of the interval. And when my Y is oriented manifold and F has no critical points, at infinity, then essentially this is the same data related by Poincare duality. Homology of pullback of good interval spectral primitive of the right end or the left end are due to each other. And finally, if we have a continuous family of maps depending on some parameter space on the same manifold, or maybe locally the same manifold, and set it all uniformly without critical points at infinity, then we can draw some kind of diagram how critical values depend on parameter, and altogether we get certain kind of complicated ramified hypersurface in product space parameters in R. So we get kind of this discriminant locus, and the homology of pairs. If you consider this pullback of some interval and relative to pullback of one of endpoints, do not change if as long as if you move this interval avoiding critical values. So we get this continuity of homology. And finally, if you deform your function and several critical values collapse, it's for some value of parameters as 0, then we get semi-continuity. The rank of a jump space at the limiting point is less than equals the sum of ranks of jumps and for nearby value parameters for nearby critical values. Okay, that is a very easy and almost trivial story, but I find it really useful to tell you, and this distinction of left and right and the duality, that's both nice tiny details. Yeah. Now we go to complex case, and I will talk about some category which is denoted by curve 0. So my target is complex numbers. So generically, if we have a smooth map with a target complex numbers, then the locus of critical values is a real curve with cusp singularities and transversal self-intersections. I usually have some kind of like standard figures in singularity theory, which project to cusp singularities, y squared is equal to x cubed, like this. so there are plenty of misprints. So it's much more complicated picture you have on target, not just discrete set of points, but this complicated figure of the singular curves. But if my manifold is a complex manifold, and the map is holomorphic and without critical values at infinity, then the locus of critical values is always a discrete subset and consists just of isolated points. It could be again finite to infinite. Yeah, but like in algebraic situation, you always have a finite set. Yeah, so it's something which you have for free in holomorphic situation. Now I just want to forget about holomorphicity. Now I'm just interested in this specific maps to C of some space for some source spaces, says that critical values is let's say a finite subset. So there's no folds. What happens in this situation? Again, by analogy with case of real numbers, we can encode topology of singularities by the following data. Recall that in one-dimensional case, when target is R, we consider pullbacks of interval relative to pullback of point one of boundary points. Interval is one-dimensional disk. And now what we do, we replace this what will be two-dimensional version. We consider smooth closed disk in C, so that its boundary point contains no critical values. It's exactly like in one-dimensional case. And we again pick one point on the boundary. And then for such thing, we can draw many such disks. And for any such disk, we consider we have cohomology of the pair, pullback of the disk relative pullback of the point. So we get this analog of one-dimensional data. And what are the properties? So it's actually a complexes, object of derived categories, and they are locally constant if we deform continuously disk and a point in the space of pairs which boundary of disk covers this critical locus. And in the situation as below, when we have let's say two disks which almost touching to each other, and we consider something like the join, we have a canonical isomorphism. It's not exact triangle, it's actually really direct sum decomposition. Yeah. So in general, one can consider some infinity category of such data, complexes satisfying these gluing conditions as above. And what is really remarkable here, there's something not infinity, but for abelian categories, if consider individual degree of cohomology, then we get just local systems of groups, abelian groups on the space of parameters. Disk is point on a boundary, such as boundary avoids critical values, and this gluing data for three disks as above satisfies the same properties. So we get abelian category. And yeah, it's a very simple point, but it cannot really don't have really good explanation. Instead of cohomology, one consider like say extraordinary cohomology theory. It's not complex abelian groups like I don't know, stable homotopy or whatever. It's still get object of this abelian category, and it doesn't directly follow from the formalism or whatever six functors. It's kind of really some kind of little work with these disks on a plane, and I don't have really scientific explanation of this. Yeah, so we get this this data of these disks, and we have a theorem which we put a long time ago with Lyudmila Tonipantia from this old paper on Hodge-theoretic aspects of symmetry. So this category, which of this gluing data, is the same as category. It's really abelian category, nothing about infinity anymore. It's category of perverse sheaves, or actually usual sheaves shifted by one. It doesn't matter which condition you put, which are locally constant on the complement to this finite set of critical values, which are denoted by sigma, and said that R gamma of this coefficient with the sheaf is equal to 0. I've considered, for example, just sheaf, not sheaf by one. You have just two cohomology groups a priori, H0 and H1. And this gives some condition which is exactly equivalent to this date of things with disks. And if we choose a collection of Gabrielov paths, which is something which I draw below, some disjoint paths going from infinity and approaching my points from the left, say, then this category is identified with the category of representation of some very stupid quiver. Namely, for each pair, set of vertices of the square is elements of this set, critical values sigma. And for any ordered pair of arrows, you get certain morphism, so you get some arrow. And the only condition is that each loop, the arrow from each vertex to itself, is an invertible map. Yeah, it's essentially like path algebra query with some localization condition. Yeah, and there are several functors from this category of 0 to categories of local systems on circles. Namely, this green points will be points of my set. Then I have a little circle around each point, and then consider the circle, and I can vary the point on the boundary. So I get a local system on the circle, on the boundary circle. Or I can consider big circle containing all points, and again vary point on the boundary. So I get many small local systems, one big local system, all on standard circles, say. And the rank of big local system is sum of rank of small local system. And if again you choose Gabrielov path, you identify one guy with direct sum of others. Not as a local system, but just fiber at, let's say, left hand of the circle. Okay. Yeah, so this is category per 0. And again, like in a real case, one have some Poincare duality. Yeah, here in real case, I recall that we have homological pair pullback of interval relative to left endpoint or right endpoint, and they are dual to each other. When my source space is oriented infinity manifold and function has no critical values of infinity. Here there's no notion of left and right. You can continuously move point on the boundary from one position to another. But for any two distinct points on the boundary of the same disk, you get Poincare duality. So that kind of really nice picture. You get kind of like local system in a circle, and for any two distinct points in the circle, fibers and have dual to each other. You get some funny notion of self-duality. And the story how it's related to real and complex story is actually a very nice elementary observation. If you get a map holomorphic or just not holomorphic, just this isolated critical values to C, and it has no critical values at infinity, then the real part of the map, which is mapped to R, it also has no critical values infinity. And jumps you can calculate through this space associated to small disks on points in complex plane, is the same real part. Okay. And now, unlike the real situation, you get some conservation law. If you have continuous family of maps with finite critical values, then this critical values again can collide, so you get less critical values for some special parameters. But then you get conservation law. Rank at the limit is equal to sum of ranks before the limit. So I recall that it's in real case you get inequality because it should, rank of jumps can only can decrease, but in complex case can never decrease. It will be just literally the same. Okay. So this is a very nice abelian category, and it actually is defined over integer numbers. And it can be categorified. So it will be some two category, and two category consists of the following thing. You get similar orthogonal decomposition of some triangular category, such that all pieces and the whole category as well have subfunctors. And main examples are Fukaya-theoretic categories. I just want to warn you that it's not the same as Schroeder. And in Schrober, you keep track of additional data, like Fukaya categories of smooth fibers, or in the Fukaya version considered homological smooth fibers. And here we completely ignore it. It's more like in our old paper with Misha Kapranov and Jan Sobelman about infrared. Yeah, this is symmetrical decomposition. Now, now I finished with this topological, general topological considerations, and now go to kind of the main body of my talk. What are how to relate to this non-holomorphic deformation of Landau-Ginzburg models? Yeah, so what was our original setup? We get a complex manifold and the holomorphic map with compact critical locus. And without any loss of generality, we may assume that critical set of critical values is non-empty, connected, and critical values are 0. Oh, sorry, the picture does correspond to what I was writing, but okay. Actually, what I wrote, it's that it's critical set of critical values is finite, and not just one critical value. And replacing y by its closure of sufficient small neighborhood, we can assume that it's y is a compact manifold with corners up to codimension 2. The picture looks like this. So we get something like a cylinder. So we get piece of it's projected to a disk and project to manifold on the boundary, and the previous will be manifold with corners up to codimension 2. And this critical locus should be some compact part. So this picture is not really adequate. I should imagine to have just one connected component critical locus projected to one point. Yeah, so here I don't assume that this y carries a non-vanishing volume element. It was a technical condition necessary for unobstructedness, but yeah, so if I don't assume that it's kind of not relevant to what I was talking about, there's no reason to think that the formal germ of derived moduli space associated to DG algebra, like we considered in my first lecture, is smooth. So you get this differentials given by commutator with a function. Yeah, so but still, because critical locus is compact, this commutative algebra form a finite dimensional space. You get finite dimensional kind of DG formal stack. And now consider family of solutions of the Markov equation. And here we keep track only of Zemo 2 grading. Yeah, this Lie algebra, it has the grading, but it's kind of accidental. Morally, it's deformation of category of matrix factorization, which is Z2 graded. There's no reason a priori for this algebra to be Z2 graded, not more than Z2 graded. But because of commutativity, it has some kind of mysterious Z grading. Okay, but let's ignore it. So consider family of solution Markov equation just purely an even part. And this can be thought as a formal non-holomorphic deformation. So what is it? It's formal series in strictly positive powers of t with coefficients in some space. Then I keep only even odd part of my Lie algebra. So consider 0,0 form. So bivector fields, or the derived differentials, or 0,2 forms, and so on. So get this thing. And satisfies this Markov equation. If this guy is convergent, assume it's convergent, yeah, then Markov equations, yeah, even without convergence, first equation gives you this identity. D bar of function plus this small perturbation by gamma component in 0,0 will be, oh, so it's not double, it's again f, it's commutator of the same f plus Beltrami differential. And if you move a little bit, this all things gamma 0,0, gamma 1 are analytic function on t, and this 0 constant term, so they could be very small, uniformly small, and if you choose some Kahler metric on my compact manifold, we can guarantee that for very small t, this at any point of my manifold, d bar derivative of deformed function, which is no longer holomorphic, is much smaller by arbitrary constant than holomorphic derivative. And here norm is choosing respect to some, let's say, Kahler metric or permission metric on compact tubular neighborhood. Yeah, so this property can be called weak holomorphicity. And it implies that the map has no, it implies that the map has no faults. Yeah, it's actually quite obvious. If the map has a fault, then it means that then its immediate calculation shows that at this point when it has a fault, this d bar derivative has the same norm as d derivative. So, so normally we should have only isolated critical values. Of course, one can imagine some kind of pathological, maybe not real analytic examples when you get maybe some countable set, some accumulation points of critical values. But in, for example, in real analytic case, you get really isolated critical values. So anyhow, we have a well-defined Fukaya-Zedel category. Fukaya-Zedel category, you don't really need homomorphism, you need kind of very weak compatibility with symplectic structure, which follows from this inequality. And because we get this isolated critical values, we can draw this Gabrielov path and get a semi-orthogonal decomposition of this Fukaya-Zedel category. Okay, all this was under the assumption that my solution of Markov-Tangen equation is convergent. Yeah, just maybe before I go on, I just want to make a little advertisement of this weak holomorphicity. So one can put the same condition for a map from, let's say, manifold of arbitrary dimension, not even to C, to have this map of weak holomorphicity, which implies it has no faults, and for such data, one can develop kind of like complex Morse-Novikov theory, which I was talking about, and you get some wall crossing and so on. And similar story one can do in other situations. For example, we have we're hearing about maybe 3D mirror symmetry. We get hyper-Kahler manifold, and for hyper-Kahler manifold, we also can make like weak version. We get not exactly integrable complex structures satisfying some big open condition, and that's it's kind of very useful. And in holomorphic theory, for example, one can achieve the situation when central charge are rational, and then one get kind of nice distribution BT invariants, nicer than generic points. Yeah, okay, so it's a sad remark. So, so my suggestion is in all situations you get kind of very rigid structure like holomorphic G2, whatever, hyper-Kahler. One should relax to much softer structures. Okay, so how to deal with this issue with convergence or non-convergence? And it will be some kind of mixed Archimedean, non-Archimedean approach, or one could say, or minimal theory, something like this. So what happens is we don't assume the convergence, which we don't have a priori. And still, I claim that one can speak about critical values. Let's again, for simplicity, assume that we are in a situation when moduli space should be smooth, when like my open manifold has trivial canonical class. Then there will be some what I explained on Euler field, and then will be multiplication by the Euler field to get some operator of homology and gets eigenvalues. These eigenvalues we call kind of like critical values in this equation. So eigenvalues are, if you consider this algebraic kind of formal family of solution Markov-Tangen equation, these eigenvalues which will be elements of some of the algebraic closure of the field of Laurent series, which are Puiseux series. So it's kind of Laurent series in fractional powers of t. And because it's we start with the situation when we have one critical value 0, the deformation is all the series start with strictly positive fractional powers of t. And let's denote for our path this collection of all distinct critical values, because these critical values can appear in some multiplicity, we just remove copies. So we get a set of distinct eigenvalues, and it's endowed with ultrametric. If you have two series, two different series, it will be some minimal power of t in which coefficients will differ, and we take like 2 to minus this power. 2 is some random number bigger than 1. Or equivalently, one can encode the structure as a symmetrized rooted tree projects to positive real line, and with coefficients of series placed at rational points of the tree. So what is the picture? It's a picture. Imagine that horizontal line, it's powers of t, which will be some rational, some 1 over d multiplied by some integer numbers. And then you draw the tree, and if you follow this tree from the left to the right to some branch, you should read some coefficients of the series. So imagine that on kind of violet points on the top, for each violet point you get some complex number. And if you follow from the left to the right along the tree, you read sequence of coefficients of your series. And at the branch point, it's a branch point. The next coefficients of series which go from this thing will be distinct complex numbers. So it means that so what's going on at each branch point we have a collection of at least 2 or 3 or more distinct numbers in complex in C, which will be this distinct first distinct coefficients of my series. Yeah, so that's a simple picture. But now, how to see it's kind of also geometrically. We can truncate our series at sufficient large degree, get polynomial in some root of t, and we get some analytic family of collection of points, and they're organized in some kind of circles. So if you keep track on the first degrees, you don't distinguish some points. So it will be some circles, and if you change parameter t, it will be rotate and shrink. Then inside the circles will be, if you make fast precision, you get another shrinking circles and so on. So you get like rotating circles inside rotating circles, and smaller and smaller size. Now that's kind of basic picture. What goes on is this collection of distinct user series. And if you get such picture, it's clear that one can speak about Gabrielov path and so on. So one can imagine that we get certain semi-orthogonal decomposition associated with Gabrielov path. So let's assume we have this unabstractedness. It's kind of basic example for us. So this will be more and more misprints. Yeah, the formal moduli space is a smooth formal supermanifold under the unabstractedness, and it's just technically cannot distinguish little misprints. Its even part is a formal smooth germ contained, and this even formal smooth germ contains certain divisor, very singular one. Divisor is defined as a set of points, some kind of parameter space where the number of critical values became strictly small as a generic point. So it gets very, very complicated singular divisor in this formal smooth germ. Now consider infinite dimensional variety of paths parameterized by this spectrum of algebra of power series, avoiding disks at the generic point, which are not entirely alike in this discriminant. discriminants. So it's infinite dimensional profile algebraic variety of a C, and it has a risky open dense domain, kind of generic part path, such that the tree of eigenvalues is the same as kind of typical point. It's kind of basic algebraic geometry, get some kind of the risky open thing. And it is a 6 maps to configuration space of first distinct Puiseux coefficients, which is associated to this ramification. So we get some combinatorial type of the tree, and for each vertex of the tree, we have kind of distinct complex numbers. Then go to next term. So we get something like configuration of associated to the tree, and namely for each vertex of the tree, you consider configuration of points in C, which will be next coefficient. So it's the product of configuration space divided by automorphism group of the tree. And so you get mapped from some kind of like infinite dimensional algebraic variety to this finite dimensional one. And on this configuration space of tree, you get shifts of various parameters. And this is a property of Frobenius manifolds, essentially related to this action of product structure, if you remember, and action of Euler field and its power, especially zero power. It implies that this is a fibration. Yeah, so it's fibers of map from path generic to any point of this configuration space associated to tree are the same, and homotopically the same. And so what we get an action of again, sorry, from this print of a finitely presented group. We consider fundamental group of this path generic, and one can show that it's reduced to some finite dimensional variety, so to the finitely presented group. It acts on the Fukaya-theoretic category, and this group maps to this pi1 of this configuration space associated tree, which is roughly product of braid groups divided maybe extension by finite group of automorphism of the tree, and the image is a subgroup of finite index. The reason is because if we have fibration of algebraic varieties, this leaves are algebraic varieties again of finite type. They have finitely many components. So you get on the level of kind of components, you get some kind of finite cover. Yeah, so we get very precise group theoretical information, some product of braid groups roughly, and some group of finite index, then something which maps epimorphism to some group of finite index. Okay, so that these things, so some big finitely presented group acts on Fukaya-theoretic category, then it maps to pi1 of configuration associated to the tree, which maps to the braid group, this index, this number of strands equal to the number of leaves of a tree. And okay, sorry, it's again misprints. And the braid group acts on the set of semi-orthogonal decompositions, and the whole picture is kind of you get some commutative diagram of group acting on automorphism category, and it's some image acting on the set of semi-orthogonal decompositions. Yeah, in principle, what we did here, we have the risky open part, avoid this bad path. And if we add this bad path, it will introduce some finitely many relations in the group. So at the end of the day, one gets still some finitely represented groups. And this is a general picture which we can extract in kind of very big generality. Yeah, so that's all which I want to say about a model. It's not really proof that a model exists, but one should work in some kind of formalism of minimal mathematics. But I think it's pretty convincing that in this situation we have A models and plenty of semi-orthogonal decompositions. What to do for B models? Yeah, so again, I just already said it. my digital algebra is kind of accidentally degraded. It shouldn't be degraded, but it is. And what follows, I'll consider deformations only in degree 0, which mirror to the Hodge locus. If it's mirrored to some, let's say, Fano variety, it's you consider part of Frobenius manifold, which is part points in comold of your variety of PP type for some virus P. And this mirror dual, it's again some kind of like diagonal part. We solve Markov equation in this space. So sum over all integers from 0 to dimension is the I power of vector fields and I power of 0, 1 anti-holomorphic forms. And here it's a crucial observation by D.Auroux. We came to it a few weeks ago, that if you get form deformation degree 0 in this Hodge locus, then we get you do something non-holomorphic, yeah, you get some D-bar stuff, but the claim that you get still a canonical scheme, which will be deformation of scheme critical loci, and together this sheaf of graded commutative algebras in non-positive degrees. And in degree 0, it will be the usual structure sheaf. So so what to say, it's not not derived scheme, it just I consider only homology. And the picture is the following. So we have this digital algebra, and it's actually factorial if you for open embedding. If you consider any open domain in U, we can map solution Markov equation in largely algebra to solution Markov equation in small algebra. And let's consider arbitrary open Stein neighborhood over point of critical locus, because it's outside of critical locus, nothing corresponds. This is constructible. Yeah, so if we restrict to open Stein neighborhood, then the algebra Stein neighborhood, it sits in degrees negative degrees 0 and 1, but nothing in positive degrees. Degrees strictly bigger than 1. The reason is the following. The differential was d bar plus commutator. Let's consider first differential d bar, because it's Stein domain, it's it will be d bar resolution of holomorphic polyvector fields, and polyvector fields are placed in degrees like 0 powers placed in degree 1, first power in degree 0, then degree -1, -2, and so on. So you see that automatically placed in degrees less than 1. And then if you solve Markov equation in degree 0 in the moduli space, so it means that element of degree 1 in my algebra, I take arbitrary element of degree 1, so get arbitrary function. There's no equation to solve. There's nothing in degree +2. So deformations are the same as deformation of the potential on the open domain, nothing else. And the claim that one can glue them together. It's not totally obvious. And then one get a global compact deformed scheme, which locally has a structure of critical locus and has derived sheaf O in degrees less than 0. So the picture is the following. When you solve Markov equation, what you look carefully what you calculate in check covering, say, instead of double resolution. And in check covering, what you do? You cover your critical locus by some Stein domain, open domains, and each Stein domain you deform function, and then on the intersection you introduce some Beltrami differential and so on and so forth. No, actually not Beltrami differential. You don't check homology. On intersection, you make some holomorphic identification close to the identity, and one can check its and then on triple intersection you do something with bivector fields and so on. But all these high corrections act trivial and homology of derived O, and they glue canonically to global sheaf of algebras. Not just not DG algebras, that's homological negatively form negatively graded sheaves of algebras. Okay, so you get actual holomorphic objects, surprisingly, and I don't know actually whether the same is true if you go to actually this is definitely not true if you go to break this condition of degree 0. It's just arbitrary deformation, even directions in modular space. For example, it's actually even clear in the case of compact manifold with no function. If you have like something like K3 surface, can deform by vector fields. You get something like quantization. So the commutative objects definitely will disappear. But in this diagonal deformation, this quantization do not appear. Yeah. So we get our canonical deformed scheme, actual scheme, with some auxiliary negative components of O. And then, because this locally looks like a critical locus of some function, we have a canonical mixed Hodge model. It's a homological sheaf of vanishing cycles. Why it's canonical? It's constructible sheaf of finite joint abelian groups, and then with some kind of Hodge structure. And some kind of Hodge structure, then we glue them, and when we glue, we don't have any continuous parameters because groups are discrete. And all these high corrections don't change anything. You get canonical mixed Hodge model. Okay, so it's now, it's where my written notes stop, and now I should take maybe 2 minutes to disconnect for a moment and connect with some other tool. And I'll continue on writing. Second. So what is what is the situation? I have so what I was talking before. A second. Yeah, I was talking about this sheaf of vanishing cycles, and manifold structure. So have so what we have deformed critical locus, yeah. And on this deformed locus, we have a mixed Hodge module, like vanishing cycle of deformed functions, yeah. So we get mixed Hodge module, and then we get R gamma of this mixed Hodge module. Oh, by the way, this mixed Hodge module is a constructible sheaf. Actually, it's before going on, something very general story. When you consider vanishing cycles, what you do, you consider preimage, you consider something homology of preimage of disk and preimage of a point on the boundary disk, yeah. Consider homology of pair, exactly like I explained in my general story. And this depends on the direction, which point on the boundary you should choose. And if you formulate algebraic geometry, you get mixed Hodge modules not on the critical locus, but mixed Hodge modules on critical locus multiplied by C star. It will be parameterize the direction of kind of boundary point. You get kind of variation of Hodge structure on this, okay, in all directions, so critical locus and C star. And then consider R gamma of this critical locus. You can keep R gamma just along critical locus, and it gets a mixed Hodge module on C star. So this get global mixed Hodge module of C star. And this global mixed Hodge moduli C star, what is it? It's just variation. It's the same as it gives you a variation of because it's no singularities here. It's variation of mixed Hodge structures. And the main point here is that for such a variation, one can define what is a spectrum. It will be analog of Varchenko's single spectrum. Spectrum is the following as the following. It will be collection of rational numbers, elements of Q, and the number of elements of collection is the rank of this variation. And what is it? When you get variation of variation of mixed Hodge structures, let me start from the other side. What is rational numbers? It's a product of Z times it's kind of integer part and fractional part. Each rational number can be composed in the rational and fractional part. So where from this variation of mixed Hodge structures we see fractional part, where we see integer part. This fractional part comes from eigenvalues of monodromy. If you get variation of mixed Hodge structures, it's well known that monodromy is quasi-unipotent, and so it gets exponent of 2 pi I P O Q goes to P O Q. And then you can, for eigenvalue of monodromy, you can produce this rational number from in semi-closed interval from 0, 1. And integer part from grading kind of term in Hodge filtration. And then we combine together, get these rational numbers. So what is technically speaking you do? You consider for each eigenvalue of monodromy, you consider corresponding sub-Hodge structure, but will be no longer interval. We will define over some cyclotomic field, and then it still carries Hodge filtration, and then we consider dimension of associated grade with respect to Hodge filtration, this component, and arranges to the spectrum. Yeah, so get this notion of the spectrum, and what I want to say that how to see this, what is semi-continuity and how we understand the semi-continuity. Let's start kind of before deformation. What we get, we still get vanishing cycles with only one critical values, and then and only critical value is 0. And here we get this spectrum. This, in fact, this is Steinberg definition of spectrum of isolated. In case of isolated singularities, you consider this variation of Hodge structures on C star and read the spectrum through Hodge theory and monodromy. Now we want to prove this kind of semi-continuity if my object is deformed, that things became simpler. So first of all, this object after deformations, after deformation, it's still well defined using this, using deformed critical locus and sheaf of vanishing cycles on it, and we take our gamma of it. Because of purity, we get again sorry, yeah, when we get our gamma of sheaf of vanishing cycles, again we get something on C star, and we can apply the definition. Okay, yeah, so it exists before deformation. After deformation in this diagonal direction, why we get inequality? And the reason is the following. I recall you this picture. Recall this picture of rotating circles. Yeah, my eigenvalues goes in some groups, and they go in other groups, and so on. Yeah. So we get this picture, and what I claim, it will have it's kind of topological picture. There will be some algebra geometric counterpart. And the picture it was kind of like a C of T maps to my moduli space, yeah, for this formal path. For any formal path, I get this picture. And what I claim is that if I get this picture, that I get more detailed information. I recall is if you have a path, then I get this collection of Puiseux series. I get collection of Puiseux series. And you get collection up to rotation of and rescaling of configurations of points in C. Yeah, so you get one collection of points and another collection of points, another collection of points, and so on. On each level of the tree, you get some collection of points. And what I claim is the following. If you look on this topologically for this homology of pairs, on each C, I get a mixed Hodge modules 0. It's kind of like this object of pair 0 with together this variation of mixed Hodge structures. Get object. And this will be algebra geometric construction. So you get this mixed Hodge modules, which I recall you gives local system, algebra geometric local system of C star for large and small circles. Yeah, so I get local system on collection of circles on each level, and then will be identification, like monodromy around small circle in one level will be monodromy of large circle of another level. It will be identification. Yeah, so that kind of story a little bit more complicated than just one. This perverse mixed Hodge module on C, but many these modules, and with certain isomorphisms of large and small, and to prove this simplification of spectra. You go by induction. You go by induction. Namely, if you get variation of mixed Hodge model with 0 R gamma on C, then spectrum at infinity kind of more complicated the spectrum at finite point. Yeah, that's actually very, very easy argument. I don't have really time to explain it. I can classify all of these mixed Hodge models, which are big mysterious objects. It's a bit you can construct from simple variation of Hodge structures, and for simple variations, it's kind of really kind of two-line argument, very cheap, shows this inequality. So sorry, about that. Okay, and this gives you very simple proof of this simplification. Actually, the proof is even simpler than what people originally designed in the case of isolated singularities, I have to say. This kind of new proof is became really trivial. Yeah, there is some little point here. You can control, first you control integer part using Hodge theory, and for fractional part you use trick invented by Warchenko. You make convolution with some roots of one and shift by rational numbers. Okay, thank you. I think I finished.
Thank you, Max. Questions?
Yeah, it's a question about something like page 14 of your slides, where you mentioned it's not a Schober.
Yes, it's not a Schober, definitely, yeah.
Yeah, but okay, categories you do not need Schober, you need only its categorification of curve zero. Now,
yeah.
But you have this non-holomorphic deformations, yeah?
Yes.
If you have the full Schober, do you have, I mean, other non-holomorphic deformations?
No, of course, this smooth fibers will be the same. You have Fukaya category with smooth fiber as well, yeah.
So then, in fact, you do have a non-holomorphic deformation of Schober as well.
Yes, yeah, definitely, yeah. But the main point here, I don't really want to consider them. Yeah,
yeah, I understand. You do not need the sheaf of nearby cycles, which do not put this cuts.
Yeah.
Okay, thank you.
Other question?
I have a simple question about concurrentiality in a complex case. So you that for points pp prime or boundary are dual. So if you take 3 points, pp prime, p double prime, which are pairwise distinct, doesn't it imply that concurrentiality is isomorphic?
No, it's okay. For each pair, they are dual. It's kind of funny situation. They're also isomorphic. They're dual and isomorphic because you just can rotate one point to the other.
Other questions? Okay, let's thanks Max again.
Okay.